Yeah, let's take a look at number 2 in section 10.8. We're going to find the Maclaurin series for the function cosine of x cubed. So the way we're going to do that is not to find the first derivative, second derivative, third derivative, and so on, and try and find the pattern to find the coefficients of the Maclaurin series, which again, a Maclaurin series is just a Taylor series where we're centered about 0. We don't want to do that. I mean, you got chain rule for the first derivative, which would be what? 3x squared times cosine of x cubed. And then you find the second derivative, you got product rule with a chain rule inside. And then by the time you get the third derivative, you got two product rules. It just starts getting really bad. So we don't want to do that. What we're going to recall that we derived the Maclaurin series for just cosine of x. We did that in class. And so here it is. And we can use this now because remember, all I have to do, notice, is replace x with what? With x cubed, right? So if I substitute x for x cubed, I simply have the x now is x cubed and x cubed to the 2n. I multiply the exponents and here it is. I'm done. I can list it out term by term. So there it is. This is the form they wanted in Achieve. There's a second question on this. It's kind of interesting. It says, use the found series, which is the one we just found, to determine the value of the sixth derivative evaluated at 0. Again, I do not want to find the sixth derivative of this. By the time I get to the sixth derivative, I'm going to have to use product rule like 5 times or something, or 4 times, whatever it is, and chain rule inside of that. It's going to be a big mess, expanding out and all that stuff. So we're not going to do that. Instead, let's just term by term list out the cosine of x cubed when n equals 0. That's 1. X to the 0 is 1. 0 factorial is 1. I get 1. When n is 1, I get negative 1, right? X to the 6th, and then 2 times 1, 2 factorial. And then when n is 2, I'll get this. 6 times 2 is x to the 12th. It's positive. 2 times 2, 4, and 4 factorial. And then I get this one and so on. I just want you to note that the coefficient of x to the 6th is negative 1 over 2 factorial, right? It's negative 1 over 2 factorial times x to the 6th, which is just negative 1/2. Now, in general, remember we define the Maclaurin series for the function, again, as a Taylor series centered about 0, so it looks like this, right? N equals 0 to infinity. The nth derivative evaluates 0 over n factorial. Remember, this was the C sub n when we're centered about 0. We derived that for the formula for generating the Taylor series, the power series representation of a function. So when n is 0, I get the 0th derivative, which is the function itself, evaluated at 0 over 0 factorial. So that this is all just the 0th derivative, the function evaluated at 0, rather, x to the 0. Okay, when n is 1, I get the first derivative, right? This is the first derivative value is 0 over 1 factorial x to the first. And then the second derivative value is 0 over 2 factorial x squared, and so on. Eventually, we'll get the sixth derivative evaluates 0 over 6 factorial x to the 6. And then it continues to go on. But what I want you to note here is, in general, the coefficient of x to the 6th is the sixth derivative evaluated at 0 over 6 factorial. So these two quantities must be the same. So if I equate these two quantities, I can solve for the sixth derivative at 0 by multiplying by 6 factorial, and negative 1/2 times 6 factorial is negative 360. Of course, you have to compute 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. I guess you can cancel the 2's out and simplify, but use your calculator and you can see that it's equal to negative 360. Okay, hope this is helpful on this one. And if not, let me know.